Welcome to day number 10 of this AIM program and the final day. So congratulations on making it this far, and you've unlocked the secret floating head video. See if you can figure out how I'm doing this. Anyways, today is about function notation, which is not that complex, but we definitely need this for calculus and lots of things. And it's not a really complex idea, but a lot of students get confused with some parts of it. So brief explanation today, and then hopefully we'll all be okay with it. In the previous class, previous video, we talked about rearranging formulas or equations with multiple variables to solve or kind of isolate, solve for a particular variable or to isolate that variable. Hopefully you remember that and you did some practice with that. Today we are doing, as I said, function notation. So it's not really continuing from the previous topic. It's just sort of a new topic. Okay. So this is from our intermediate algebra textbook 3.5, chapter 3.5. I'll just explain the idea, the concept of function notation first, and then we'll go on to some examples. So let's say we have three different functions like this. Y equals 3x plus 7, y equals negative 2x plus 14, y equals 0.2x minus 4. So often we would deal with these sort of as lines on a graph, and then one of them looks like this, and another looks like that, and another looks like this or something. Right? They'd be straight lines on our graph. We don't always deal with them like that, though. And let's say, for example, I want to know, well, what is one of them when x is equal to 3? What is the first one? So how do I write that? Do I say like this one, when x equals 3, and then we evaluate it down here or something? Because all of the functions here are all just in terms of w, sorry, not w, y, we don't really have separate names. So there is function notation gives us handy names for these things and helps us differentiate them. So let's say we turn them into this, and we say instead of this, we'll say that this y equals f of x, and in this case, y equals g of x, and in this case, this y is equal to h of x. Then we can rewrite these things like this. And then we have different labels for them. This 3x plus 7, well, this one we're calling function f. This negative 2x plus 14, we are calling function g. And this 0.2x minus 4, we are calling function h. So now if I say, well, when x is equal to 3, I can say, well, I can write it like this. Function f when x is equal to 3, and then let's just directly evaluate it. We don't have to write out statements of like when this is that or whatever. So gives us a name, and it's an easy way to say this function at this value and refer to that. So that's the benefit of it. Just so you know how we read this, I'll formally state this here. So this thing on the left would be read as f of x, and then g of x, or h of x. Or we could read it like this. The value of f, again, f is a function, the value of function f at x. That's basically saying, like, what is the value of function f when x is, or when evaluated at x, when we put x into that function. So that's the idea. and that's how we talk about it. So f of x, or value of f at x. Let's actually do that evaluating with some examples here. So first set that we have and we'll talk about is here. So we have this function where we have defined f of x to be equal to, forgot to mute my phone. Nope. So f of x is equal to 2x squared plus 3x minus 1. And we want to know, what is this function equal to first when at f of 3, so when x is equal to 3, or what is it at f of negative 2 and at f of a. Okay, so basically we're just substituting in. We're going to take this 3 and we're going to replace each value of x with the 3 here. But I'm going to write one extra step before that, because that will help us with the harder problems in the next set. So let's take our function here and let's rewrite it this way. So f of x equals 2 brackets, or parentheses, x squared plus 3 in parentheses x minus 1. It's the same thing. We haven't changed anything. We haven't done any math here. All we did is take the thing that is sort of inside the function here and just put brackets around that. It made that very clear that that's sort of a separate part, and that can change. If we evaluate the function at some other values, that part is what's going to change. So let's do this. And then we'll do this for a here. So for a, which we said is f of 3, we don't actually need to do that. We'll just write equals directly here. So f of 3, I'm going to do different colors to help us. F of 3 is equal to, and then each set of brackets here, I'm just going to put that 3 in there. So 2 brackets, 3. I'm going to do all the blue stuff first. It'll be easier so I don't have to keep switching colors. And 3. Okay, so each x, 1, 2, 3, has been replaced with on the left side and on the right side. Now we can just evaluate. So 3 squared is 9 times 2 is 18, plus 3 times 3 is 9 minus 1. So that's 27 minus 1, 26. Okay. Our next one, making sure I space. Okay. Part B. So f of negative 2. This is equal to, we're going to do the same thing, take our original function and just inside each kind of pair of parentheses here, we're going to replace that with our value here of negative 2. So that's 2, and then I'm just going to put the negative 2 in after, so I don't have to change colors of my pen so much. Negative 2 and negative 2. And then we evaluate. Negative 2 squared is 4. Positive 4 times 2 is going to be positive 8. This is 3 times negative 2. That's actually minus 6 there, and then minus 1. So result is just 1. All right. And C is actually going to be the easiest one here. F at A. We are just going to replace each x with a. So 2 squared, 2a squared plus 3 times a minus 1. A. And we actually can't do anything here because we don't know what a is. We can't simplify this. So we can just rewrite without these brackets because they're not necessary anymore. Plus 3a minus 1. That's it. So there is f at 3, f at -2, and f at a. We've evaluated all 3 of those. Okay, so again, these are the easier examples. We'll see how this method helps us with the harder ones in a moment. But first, our typical practice, my turn, and then your turn next here. So let's rewrite f at x equals 3 x squared minus 2, and then parentheses x plus 1. So our first one, f at 3 is equal to 3 times 3 squared minus 2 times 3 plus 1. 3 squared is 9 times 3, that's just 3 cubed, that's 27, and minus 6 plus 1 here. So that will give us 18. Did I write numbers? Yes, that looks okay. All right, our next one here. Yeah, okay. And something, I think I had a mistake in my notes, but this is correct. Our next one, B here is f at -1, 3 times -1 squared minus 2 times -1 plus 1. So that's -1 squared, +1, that's just 3. And then minus 2 times -1, that's +2. And 1, 3 plus 2 plus 1 is. And our last one, part C here, again, the easiest. F at t is just 3t squared minus 2t plus 1. And we can rewrite without the brackets. 3t squared minus 2t plus 1. Okay, that's it. So there are the 3 that we were asked to evaluate here. That's my turn. And your turn with this function. Still pretty similar, still pretty easy. So take a moment, figure this out, and I'll see you soon. Right. To hide my pen tool behind my face. All right, so our first one here, part A, which is f at 2. I'm just going to go to my notes, and my answer here was 13. For part B, f at -3, my answer was +3. And part C here, my answer was f at h. That's the whole thing. It's 2h squared plus 4h 3. Hopefully you got the same results. Okay, that's this part. So now let's look at some slightly more complicated situation, and this is the part where students usually get tripped up. So let's make sure we can do this well, and then one more set of examples after this. Okay, so we have some slightly more complex situations. We have g of h squared, so a squared term inside there. We have g of x plus 2, and we also have g of x plus g of 2. So if you want to try thinking right now, g of x plus 2 and also g of x plus g of 2. Will these two things be the same, or will they be different from each other? Without evaluating them, like, are they necessarily the same thing, or is it possible for them to be different? Okay, so let's take our function here and we will rewrite g of x and equal to 3. Just like we did before, I'm just going to take the x and put it in brackets, because that will make it much easier for us to see where we are substituting these things in. So part A, g of h squared. So anything where we have x, we are going to rewrite to have h squared. So g of h squared is equal to 3 of h squared, 3 times h squared, minus 5. And then here, there's nothing to evaluate. We'll just rewrite without the brackets. 3h squared minus 5. Okay, our next one, part B here. So g of x plus 2. Again, we'll take our brackets and just the thing inside here. Let's rewrite x plus 2 in our colors, x plus 2. And the thing that's inside the brackets here, we're going to replace whatever's inside the brackets in our original function with that. That's all we have to do. So we'll have 3 brackets. I always say brackets, parentheses, of x plus 2 times x plus 2 here, 3 times x plus 2 minus 5. So now we do actually have some work to do. We can expand this and simplify. So 3x plus 6 minus 5. Very simple to simplify. 3x plus 1 here. Okay, and then our last one. So get your money in now. Do you think C, the result for C will be the same, or will it be different from part B here? So part C, I didn't need that one. We are doing g of x. Let's do colors. G of x plus g of 2. X and 2. Okay, so to do this, we will have our function basically twice. It's written here, g of something, and then plus g of something else. So we need our function twice. So we will have 3 times x minus 5. That's the g of x part there, and all of that plus, then again, we will have our g of 2. So that is 3 to which minus 5, like this. So this one here is representing g of x, and this one here is representing g of 2. So we have the function twice there. Now we just expand and simplify. So this is, these first brackets aren't doing anything. This is just 3x minus 5 plus, and then 3 times 2, 6 minus 1, so plus 1. Okay, so then this is just 3x minus 4. So let's compare. Part B was 3x plus 1, and part C was 3x minus 4. So it turns out that these are not equal. We cannot assume that these two things will be equal ever. It might happen sometimes, but probably most of the time they will end up being different. But there's no automatic assumption or reason to believe, like we can't, there's no like proof. It's not an automatic thing to say they'll be equal. We have to actually evaluate both of them and compare if we do want to know that. Okay, so they're distinct things, separate things to evaluate. All right, so that's the more complicated one. So as usual, here to my turn. So g, just to help us see this, g of x is equal to 4x 7, just adding in our parentheses here. All right, a. So g of, I'm not going to keep doing the colors because it slows me down too much when writing them. So g of m squared is equal to 4 times m squared 7. So that's just 4m squared 7. B here is g of x minus 3. So again, anything inside the brackets, I'm just going to replace and write x minus 3. So 4 times x minus 3 minus 7. Expand and simplify here. 4x minus 12 minus 7, so negative 19 here. And then c over here. G of x minus g of 3 is equal to g of x, so that's 4x minus 7. Add our brackets for clarity here, minus, and then g of 3 will be 4 times 3 minus 7 here. Okay, and then our results will have 4x minus 7 minus 12 minus 7, that's 5, negative in front. Okay, so that looks like 4x minus 12. Okay, that's this one. And now one practice one for you. Go ahead. All right, so we're back. Move my pen thing again. Right, so our answers here for part A, h of k squared is just 2k squared plus 1. B, h of x plus 1 is, my result here was 2x plus 3. And C here, h of x plus h of 1. That's not a 1, that's 1. And this worked out to be 2x plus 4. Again, please note, B and C, different results here. Even though both of them are sort of h of, there's an h of x and an h of 1 and a plus, but they're grouped in different ways. So different things we're calculating. Okay, that's the second set of problems done. Hopefully you got the same results I did here. And then the last one. This is actually our first time looking at word problems in this this whole program, actually. So let's do that. Just take a moment and read the problem here. Okay, so hopefully you've read it and it kind of makes sense to you, and you can see what we're trying to figure out. So number of unread emails in Sylvie's account, we've got a 75 here, and it is growing by 10 each day. We'll get bigger by 10 each day. Okay, so we have a function n of t, and that is equal to 75 plus 10t. Well, what are these things? N is the number of emails, unread emails, n, total number of unread emails, and then t is just measuring time, specifically in days. Very important to know our units here. So n and t. Okay, so first determine the independent and the dependent variable. So when we graph a relationship like this, normally we have our independent variable on the x-axis here, the horizontal one, and the dependent variable on the y-axis. So we want to know which one is which one is independent, which one is dependent. This isn't always the relationship. We could have like codependent variables or something, but most of the time, one is independent and one is dependent. So in this case, which one is which? So which one depends on the other? Does time depend on number of emails, or does number of emails depend on time? So if time depends on emails, emails is the independent thing and time is the dependent thing. That would mean that the number of emails, unread emails in her account is just growing on its own, not dependent on time. But time is dependent on that. So it's crazy to say, but what that would, the relationship in that case would need to be that the time does not proceed. Like we don't get a new day until she has at least another 10 unread emails. So until she gets an extra 10 unread emails, the sun does not go down and it does not rise the next day. Okay, that's crazy. Like the sun does not care. The rotation of the planet does not care about how many emails she gets. Let's think about it the other way, where the number of emails is dependent on time. So time is independent, is just moving and increasing on its own. And as time increases, emails keep coming in and she keeps not reading them. So that makes more sense. Time is progressing on its own, but dependent on that time. As time increases, and she gets emails. So that second relationship makes sense. So independent variable here on our horizontal axis, this would be t for time. And on our vertical axis for our dependent one would be n. There's no like math shortcut or whatever to know which one is dependent and which one is independent. You just have to think about the real world relationships between those two things and then what makes sense. What best describes the relationship between the two variables. Okay, so T is independent. N is our dependent one. And the second thing, they are asking us to find n of 5. So using our function notation here, nice handy label, instead of just like y equals something, we have a label n for number of emails. So original function n of t equals 75 plus 10t, and we are being asked to calculate n of 5. 75 plus 10. How do we do this? We just replace the t with that 5. So 10 times 5. And when we do that, we get 75 plus 10 times 5, 50, so 125. So n of 5 is equal to 125. So that math there is quite simple, but they're also asking us to explain what this result means in terms of the variables and the actual relationships that we have in the problem. So 25 means that after 5 days have passed from the starting point where we start with 75, so after 5 days, she will have total 125 unread emails. That's how we take this math result and interpret it in a real world context, given the situation of the problem here. Okay, so again, n equals 5, or n of 5 equals 125. That 125 represents the number of unread emails she will have after 5 days, given the growth pattern that we've been given here, growing by 10 each day. That's it. So let's, unlike the previous days, I don't have another one for me, just this one. So now you try to do the same thing with this problem here, and see if you can. Okay, so hopefully you got the same results I did here. For this one, I found that n of 7 is 100 plus 15 times 7. This works out to 205. And if we interpret this, this is the almost the same kind of problem. This is the number of unread emails that Brian will have in his account after 7 days. So number of total unread emails after 7 days. That's the interpretation of the problem. Independent and dependent variables, it's the same as the other one. T is independent, number of days passed, and dependent is our capital N, which represents number of unread emails. Okay, hopefully you got the same result. I guess I should write out a sentence or something for that, but I'll just save us some time here. Okay, so that was it for the problems. In our textbook, the Intermediate Algebra textbook 3.5, if you want to do some practice with just substituting in single numbers or single variables or whatever into a function, you can do that with these problems here. If you want some practice substituting in multiple terms like g of x plus 5 or something, that is in these problems here. Mixed practice, just kind of a bunch of different sort of functions at different values. That's here. And then some word problems. Again, first time we've done this in this program, but definitely important to be able to read. Those are here. Not too many of them, but a few. So get some practice with function notation there. And yeah, I guess I should have another slide like saying congratulations for watching all the videos or something. Whatever. Hopefully this program was useful for you, this video, and then also the whole program. There are quizzes you can do to test how well you've actually been learning the material, and there should be a kind of final test as well, kind of feedback for me if you've acquired this information well. Thoughts, feedback, whatever, please send me an email, which I don't have on the slide here, but it'll be in the program description and notes. And otherwise, I will just see you when the new semester starts for real in our regular Mathematics for Business class. Thank you for watching.